As the demand for cloud-based data continues to increase, data centers are migrating from 100 gigabit Ethernet to 400 gigabit. As the cloud needs to support more applications such as video streaming, 100 gigabit PAM4 has become a popular choice for optical technology. Optical fiber interconnects are a key part for this technology. These have become the preferable choice for data centers with the ever-growing demand to increase speed and reduce power. As a system design engineer, have you been able to analyze your entire link from electrical to optical back to electrical passing through different domains? As a system designer working on TOSA or ROSA transceivers for optical interconnects, have you simulated your design in the complete link within a given bit error rate target? Can you characterize the transceiver performance with a modified set of parameters, such as varying levels of laser power or different lengths of fiber? Have you been able to view performance changes with these modified set of parameters? Keysight Technologies, partnered with VPIphotonics, has created the industry-first integrated workflow that allows system engineers and electrical engineers to analyze the entire optical link end-to-end. Let's address challenge number 1. Analyze the entire link from electrical to optical back to electrical passing through different domains. In this video, we will cover these main challenges with a typical 400G base FF4 transceiver, a full end-to-end link. So how do we address challenge number 1? PathWave ADS is the platform that drives the E-O-E analysis, where the electrical and optical parameters are exposed. This simulation is not static, but dynamic, meaning that when the simulation is running, VPI Design Suite is called to process the electrical signals from ADS, returning it back to ADS in an interactive manner. The electrical systems are represented by ADS, and the optical by VPI Design Suite. This side here represents the TX AMI, generating the PAM4 signal, and the other side, the receiver, where CTLE is applied. The 3 eye probes as seen here is where the data is collected. Here are the results, 3 eye diagrams, one at the redriver output, one after the optical channel, and one at the receiver output after CTLE equalization. Challenge number 2. Simulating the design and the complete link within a given bit error rate target. This is using the same workspace example as previously shown. Here are the results. The results show the eye diagram at different number of simulated bits, as well as the timing and voltage bathtub currents with the bit error rate contour. With the bit error rate plots, you can run 8,192 bits, 1 million bits, and 10 million bits within a reasonable simulation time. As the number of bits increase, the eye will close due to random jitter. With the increased number of bits, you can also calculate the bit error rate in a more accurate way. Let's take a look at the third challenge. Characterize transceiver performance with varying optical parameters. In this example, we are looking at the ADS workspace that performs a parameter sweep. Let's take a look at the VPI optical component in ADS. Here is where you can enter in the optical parameters by setting up variables and running a parameter sweep. You might be wondering, how are these parameters getting read into ADS? The optical parameters are coming in from VPI Design Suite back into ADS. Let's take a look at what it looks like from the VPI Design Suite side. Note, the optical parameters here under the ADS tab. Let's return to the simulation results. You can use the arrow keys on your keyboard to sweep the values for fiber length and laser power to view the changes in the eye. You can also view the eye height and width based off of a specific bit error rate, as well as VSR PAM4 measurements. In addition to the 3 main challenges that we solved using Keysight's electrical solution, you can also perform advanced PAM4 measurements, including TDECQ and jitter. PathWave ADS connects to the FlexDCA oscilloscope using the FlexDCA probe and takes in the simulated waveforms from ADS.